Our second module will focus on fuels for exercise. As we saw in the lectures on muscle, ATP is essential for muscle contraction, and ATP is required for a number of the important cellular processes that maintain membrane excitability, calcium homeostasis, and the ability to generate force during muscle contraction. The energy systems that are present in skeletal muscle are designed to generate ATP. Traditionally, we refer to them as the anaerobic energy systems, or substrate level phosphorylation that's not dependent on oxygen. The other pathway is oxidative metabolism, or oxidative phosphorylation, where ATP is generated in the presence of oxygen following the breakdown of carbohydrate and fat primarily. Proteins, under certain circumstances, can be utilized, but in most instances they represent a relatively small proportion of the overall energy metabolism during exercise. As the name implies, substrate level phosphorylation involves the transfer of phosphate across substrates. Phosphocreatine is another high energy compound found in skeletal muscle, and it can be used to rephosphorylate ADP to ATP in a reaction catalyzed by the enzyme creatine kinase. You see here that creatine is important in that reaction, and creatine supplementation is popular amongst athletes, particularly those involved in high intensity efforts for that reason. Another important reaction within skeletal muscle is that catalyzed by the enzyme adenylate kinase, where two ADP molecules can come together to produce ATP and AMP. Obviously, the ATP can be then utilized. AMP can be broken down further to a compound known as IMP, and that has implications, particularly during high intensity exercise, for fatigue, and we'll come back to that later on. The other important series of reactions is glycolysis, whereby glucose molecules, either from muscle glycogen or from glucose in the bloodstream, is broken down in a series of reactions to pyruvate, and under intense exercise conditions, that pyruvate is converted to lactate. If we consider aerobic ATP production, then we need a number of precursors, and we need oxygen. In the module on the oxygen transport system, we'll look at how the heart and the lungs deliver oxygen to contracting muscle, and clearly you need oxygen in the mitochondria. You need ADP, an inorganic phosphate, and they are produced when muscles contract and ATP is broken down. And you need electron donors, and these are derived from the metabolism of fat and carbohydrate, and we'll examine those in our next lectures, how fats and carbohydrates are utilized. And these electron donors ultimately transfer their electrons to oxygen in the electron transport chain, setting up a proton gradient which then fuels or powers the resynthesis of ATP in the mitochondria. An important concept in exercise physiology is the relative power and capacity of these energy systems. As you can see, ATP is generated very rapidly from the breakdown of phosphocreatine and through glycolysis. The rate of ATP production is lower when you oxidize carbohydrate, and lower again when you oxidize fat. And this explains the often made observation during prolonged endurance type events, when athletes run out of carbohydrate, or often described as hitting the wall, they have to slow down because they rely more heavily on fat with a lower power output. In contrast, the capacity of the systems is inversely related to the power. You can see that the phosphocreatine hydrolysis and glycolysis have a very low capacity for generating ATP, the total amount of ATP that's generated. This is the trade-off for the high power. Carbohydrate oxidation has a finite capacity because there's a limit to the amount of carbohydrate that we can store in the body. In contrast, the major energy store in the body is fat. And even in the leanest of endurance athletes, they have more than enough fat to keep them going effectively indefinitely, provided they continue to maintain adequate nutrition, of course. So the capacity of the system is inversely related to the power. If we now look at some examples of how these energy systems are utilised, let's look at the transition from rest to a certain level of exercise we call steady state exercise. And in this example, an exercise intensity that requires about 1.8 litres per minute of oxygen. You can see that the oxygen uptake doesn't increase instantaneously to that level. There's a lag. And during that period where there's a difference between the amount of energy coming from the aerobic energy system and the energy requirement of the exercise, you can see that substrate level phosphorylation, primarily the breakdown of phosphocreatine, but also a contribution from glycolysis, makes up that energy shortfall. And this area here we often refer to as the oxygen deficit, and we'll come back to that in the module on oxygen transport. There's a similar oxygen deficit when you transition from one level of exercise to a higher level of exercise, and there would be a similar adjustment. If we look at very intense short duration exercise, in this case lasting only about 30 seconds, you can see here the relative contribution of the three main energy systems in such an exercise bout. Early on, there's a primary reliance on the breakdown of phosphocreatine, a significant contribution from glycolysis, and a small contribution from oxidative phosphorylation. As the exercise duration increases, there's a gradual increase in the contribution from oxidative phosphorylation and a decline in the contribution from phosphocreatine. The anaerobic glycolysis is reasonably well maintained, and then it too also falls off. If we look at more prolonged strenuous exercise, so-called endurance type exercise, then really it's the carbohydrates and the fat utilised in the mitochondria in the presence of oxygen that contribute the majority of energy. And you can see that we have stores of carbohydrate and fat both within the muscle and outside the muscle. The muscle glycogen stores are very important, and they have about 1,000 to 3,000 kilocalories of energy. There's also glycogen in the liver, and although the concentration of glycogen in the liver is greater, because of its smaller mass, the absolute amount of glycogen stored in the liver is less. It has an important role, though, in maintaining the blood glucose level, and this glucose can be taken up by contracting muscle. Some of the lactate that's produced during exercise, in turn, can be taken up by the liver and converted to glucose in a process known as gluconeogenesis. We'll talk more about this in the next lecture on carbohydrate metabolism. In relation to fat, this is the primary energy store within the body, most of which is found within the adipose tissue. And the triglycerides stored in the adipose tissue can be broken down, liberating glycerol, which can also be used in gluconeogenesis in the liver, but importantly for contracting muscle, the free fatty acids, which travel in the bloodstream and can be taken up by the contracting muscle. There's also a store of triglyceride in the muscle. And again, the concentration is less, but because relatively more energy is stored per gram of fat than gram of carbohydrate, there's a significant amount of energy stored in the muscle triglyceride. And in the final lecture on fuels, we'll look at fat metabolism during exercise. The primary determinants of the relative contribution of carbohydrate and fat to exercise are intensity and duration. If we look at the effect of intensity, as exercise intensity increases, what we see is an increased reliance on carbohydrate, both blood glucose, but importantly, muscle glycogen, such that at the higher intensities that you often see during competitive endurance type events, there's a very heavy reliance on the muscle glycogen stores. And we'll come back to this a number of times in relation to carbohydrate metabolism and also in relation to fatigue. If we look at fat metabolism, you can see at the low intensity a very important contribution from fat. As exercise intensity increases, the contribution from fat goes up a little bit, but then it comes down at the higher intensities, consistent with the greater reliance on carbohydrate. And in the later lectures, we'll investigate some of the mechanisms that are responsible for these interactions between carbohydrate and fat metabolism. If we look at exercise duration, and in this case, about 4 hours of exercise at about 70% of the maximal aerobic power in trained cyclists. And you can see at this intensity and at this duration, most of the energy is coming from carbohydrate. Over time, however, as the muscle glycogen levels go down, the reliance on the muscle carbohydrate, muscle glycogen stores decreases. There's an increase in the contribution of plasma glucose and an increase in the contribution from fat. But eventually, at this exercise intensity, the rate of carbohydrate oxidation falls to a level that means that the subject is unable to maintain this level of intensity. We'll talk more about that in relation to fatigue. But as you can see, over time, carbohydrate oxidation tends to go down and fat oxidation goes up. As I said, the main factors influencing exercise metabolism are exercise intensity and duration. These can be influenced by the preceding diet. A high carbohydrate diet tends to promote the oxidation of carbohydrate, and a high fat diet appears to promote, or does promote, the oxidation of fat during exercise. An important adaptation to training is a reduction in carbohydrate utilization at a given power output after training. Increases in environmental temperature tend to increase the rate of carbohydrate use, and age and gender can also influence the relative contribution of carbohydrate and fat. It's generally thought that females rely more on fat during exercise, and this appears to be related to the sex hormone estrogen. And these effects are mediated by substrate availability, hormone levels, and the biochemical characteristics of the skeletal muscle, which determine its ability to oxidize fat and carbohydrate.